Hi and Assalamualaikum to our respected lecturer, Dr. Ahmad Muhammad, the lecturer for Theory of Structure in September 2020 semester. We are Group 1, that is, consists of 5 members, including myself, Adam, as the team leader. My other colleagues are Nabil, Harith, Reva, and Oscar. We have been working together since the second week of this semester on this project that discuss about the dynamic load on high-rise building. And the high-rise building that we are talking about is the Exchange 106. I will tell you a little information about this tower. The Exchange 106 is a skyscraper located in Kuala Lumpur, Malaysia, within the Tun Razak Exchange TRX zone. It was completed in 2019 and standing tall at 445.5 meters above from sea level, make it as the third tallest tower in Malaysia after Petronas Twin Tower 1 and 2. During the early stage of building this high-rise tower, the engineers has already taken into account the dynamic load that will act on this tower. One of the example is the wind loading. The real wind is turbulent. It will do massive damage to a building when the speed is very high. We can say that this newly raised building is actually obstructing the wind passage. So we have to build it in the behavior so that it can withstand the wind load. In some cases, the top floors of the building will displace for several meters if the wind is blowing very hard. This event will cause discomfort to the people who are at the top floors of the building as they are in the motion along with the wind. This also will cause structural instability and can lead to structural failure. This can be fatal to the thousands of people in and outside of the building if the building fails to withstand the wind load. Wind loading can be very complicated for a high-rise building, and so these systems are mostly constructed based on the behavior of a building model measured in a wind tunnel. It is important to consider the wind hitting the structures from either direction while doing so. The effects of wind-generated lateral loadings can lead to raking or leaning of a building frame. Engineers often use cross-bracing, knee or diagonal bracing, or shear walls to resist this effect. Earthquake loading. Earthquakes give rise to dynamic loads with high potential for catastrophic result for structures as well for people. There are various aspects in which the structures are influenced by earthquakes. The earth vibrations is the most prominent, but not the only one. Other earthquake effects include ground collapses such as liquefaction, that is, loss of the strength of silt or sand layers due to build-up of pore water pressure, landslides and mud flows, usually caused by liquefaction. Further effects include sea wave, that is tsunami, and lake wave, sea chase. The risk of earthquake shaking the high-rise tower, a solution that was implemented in Shanghai World Trade Center, can also be implemented to another tower. 2 active mass dampers installed on the top floor of the tower. Those dampers counteract whiplash by pushing their 150 tons counterweight in the opposite direction, reducing sway during earthquake and typhoons to just only 1 meter at the top floor. Dynamic load that we will discuss is loading from explosions and impact. Blast and damage loads are thousands of times higher in subsequent length and severity than all other loads in the structure's construction life. The main contributor to this load is other building detonation around it and also terrorism attack. We can see this already happened in 9/11 tragedy in US. This tragedy has brought another concern to engineers' mind all over the world. During designing stage of a high-rise tower, they have to make sure their designed tower can stand even after it was hit by a jumbo aeroplane. Some towers also come with refuge floors for the resident to refuge in case something bad threatens the tower. For the next part of the presentation, I will hand over to one of my colleagues, Nabil, to take over the presentation.
Hi, my name is Nabil Iman and I'm presenting question 2. So for question 2, there are 3 things to consider: the dead load, live load, and the type of slab. So for the dead load, we are calculating a reinforced stone concrete 100mm thick with the density of 23.6 kN per meter cube. For the life load, since TRX 106 is a office building, the life load will be a minimum of 2.4 kN per meter square. And for the slab, we have to find out what type of slab it is, so we'll be figuring that out in the next slide. So to find out if it's a one-way or a two-way slab, we gotta see the B and A, which are labeled on the diagram on the right. So if B over A is more than or equal to 2, then it's a one-way slab. If it's less than 2, then it's a two-way slab. And the picture below, bottom left, shows how it would react under load. So in our case, we have a two-way slab since B over A is less than 2. That means the tributary area will be hexagonal. You can see from the picture on the top left. So first we gotta find the distributed load, aka total load. This is comprised of the day load and the live load. So the day load is the concrete. We take 23.6 kN per meter cube, which is the density of the concrete, and times it by the thickness, so we get the distributed load. We add that with the office distributed load and we get the total load. So to find the distributed load on the beam BE, we take the total load and times it with 2.25, which is the length of A. And then you can see the shape of the distributed load is like a pyramid with a cut-off top. And from this diagram, from this free body diagram, we can calculate the reactions BY or EY, which is 10.04 kN. And for FED, we have the same thing, except the distributed load is a different shape. It is two triangles next to each other. You can see that from the top left picture. To find the distributed load, we times the total load with 1.125, and then from there we can find the reactions Fy and Dy, which is 22.1 kN. That's all for me. Thank you.
Thank you, Nabil. For now, I will explain on how we can find max deflection by using moment area method. So first of all, we draw the bending moment diagram. And from this bending moment diagram, we can find moment equations on each section of the beam. After that, we draw the deflection of the beam. Now, before we draw the deflection of the beam, we need to visualize on how the beam would form after the distribution load is acting upon it. And we can formulate a formula on finding the deflection from the drawing as well. So after finding the formula, we can calculate the deflection of the beam by finding the area and the centroid of each section in the bending moment diagram. That's all from me. Thank you.
Hello everyone. My part in this project is question 3 to find out the deflection of beam at BE. I used the double integration method to find out the deflection of beam. First step is find the moment equation. The diagram was cut into parts to find the moment equation. The reason why the third section did not cut because it has same distribution of load as part 1, which is first section. With that equation, we integrate it twice, which is called double integration. Later we assume the boundary conditions. Next step, assume the max deflection at center and found out the value of x, which is 0.375. And finally, the maximum deflection is calculated. Thank you.
Good afternoon, my name is Lim Xin Yu and I'm going to talk about the lateral buckling. Imagine this is a beam and apply force on both ends. It starts to bend. This is what we call lateral buckling. It's a phenomenon where columns and beams deflect sideways due to excessive compressive loadings. In the case of high-rise building, There are few dynamic loads. They will apply force to the beams from the horizontal side. It will cause it to buckle. When discussing about lateral buckling, we have to know what is a critical load. The critical load is actually the maximum axial load before buckling, which means if the load exceeds the design critical load of the beam, it will cause the beam to buckle. The critical load can actually be represented by a mathematical formula, which is the pi square times the modulus of elasticity times the moment of inertia divided by the effective length squared. Now we'll talk about these factors in detail. First, the modulus of elasticity. The modulus of elasticity is a quantity that affects an object's resistance to being deformed elastically. Different objects, different materials, it will give different modulus of elasticity. From the formula, we can see that the higher the modulus of elasticity, it will gives you higher design critical load, which reduce the tendency towards lateral buckling. Next, we will talk about the moment of inertia. The moment of inertia is actually a measure of the resistance of a body to an angular acceleration about a given axis. As we can see from the formula, the higher the moment of inertia will also gives you greater resistance towards lateral buckling. The moment of inertia is actually affected by the shape of the cross-section, which we will discuss later. Okay, now we'll move on to effective length. Effective length is actually defined as the length between points of inflections on the buckle shape. We can understand it through a mathematical equation, which is effective length equals to effective length factor times length of the beam. So the effective length is inversely proportional to the critical load. Hence, we want lower effective length as possible. Given the length of the beam is constant, we always want lower effective length factor, which is affected by the type of supports of the beam. Now we'll move on to solutions to prevent lateral buckling. First, we have to choose materials with high modulus of elasticity. For example, steels. Steels are known for their high elasticity, as high as 200 gigapascal, and is commonly used in construction these days. And reinforced concrete, which is also consists very high modulus of elasticity, because it's a concrete reinforced with steel, and it gives you greater resistance towards lateral buckling. Next, the shape of cross-section. We have to use shape with high minimum moment of inertia. To achieve that, we have to, given the total areas of a shape is constant, it's desirable to have like circle shape or square shape, because the mass of the shape is uniformly distributed. So the moment of inertia of all axes are almost the same, and will gives you higher value. Besides, we also can use hollow shapes such as I-beams and hollow cylinder beam. This is because when the mass of the shape is away from the axis, it gives you higher moment of inertia. So it's desirable to have this shape as your cross-section of the beam. Next, we'll discuss about the type of support. As mentioned before, the type of support affects the effective length factor, which range from 0.5 to 2. The fixed end support will give you 0.5 of effective length factor, whereas the free end will give you 2 as your effective length factor. It's desirable to have lower effective length, which will gives you higher critical load and then makes your beam more resistant towards lateral buckling. That's all for my presentation. Thank you.